Do we all remember the COVID-19 pandemic from a couple of years ago? It touched each of our lives in one way or another, and we're still very much dealing with the effects of it today. It changed society and the world as we know it, and it led to the widespread implementation of public health measures such as masking and social distancing. Now, these measures worked, but as climate change progresses and the population continues to grow, the risk of pandemics posed by respiratory viruses such as COVID-19 continues to change and grow as well. This connects to TICED's fourth theme of adaptation and resilience in the face of climate change. So the question is, how do we mitigate the spread of these viruses so that we can stop the next pandemic before it happens? Well, to do that, we have to look at how these viruses themselves spread. Respiratory viruses, like COVID-19, spread through respiratory fluids that exit our body when we talk, laugh, cough, sneeze, or even breathe. These fluids can exit our body as large droplets that can settle on surfaces and lead to indirect contamination, or as small aerosols that can stay in the air for an extended period of time and travel even further. So, the shape and size of these droplets dictates the route and range of transmission. Therefore, in order to develop accurate virus transmission models, we have to understand the factors that affect the shape and size of these droplets as they leave our body. Looking at the structure of the fluids themselves, respiratory fluids, such as mucus, are composed of proteins called mucins that are suspended in water. In the presence of viruses, these networks can shift and change, which affects the size and shape of the droplets that we produce as they leave our body. This is the phenomenon that I aim to focus on with my research, and here are the first two parts of how I intend to do that. First, I want to use rheology to analyze the different forces that impact the shape and size of these droplets as they are generated within our body and exit. By using suspensions of respiratory fluids, as well as different types of nanoparticles to represent different viruses, I want to look at how these forces change and how the shape and size of these droplets changes looking at specific fluids with specific viruses. Next, I want to use a custom fragmentation chamber that is both temperature and humidity controlled to look at the sprays themselves. Using a high-speed camera, I hope to get images such as these and compare them under different climate contexts. This also allows us to extend the scope of this research to not just be applicable within a Canadian climate context, but globally. Together, this information should help develop more robust virus transition models, which will enable our healthcare system to implement the most effective public health measures when necessary so that we can stop the next pandemic before it starts. Thank you very much.